This is ELC131, Circuit Analysis 1, and we'll continue on the topic of power in this video, talking about horsepower and efficiency. Now, when we think about electrical energy, work is produced by creating an action. Work, by definition, equals force times distance. And this work can either be in the form of thermal work, light, or mechanical work. And we're concerned with, in this presentation, talking about mechanical work and the horsepower. The horsepower is used to measure the output power of motors. The symbol for horsepower is HP. The term was invented by James Watt as a means of comparing the output power of his steam engine to that of horses. James Watt defined 1 horsepower as the amount of work done by a standard size horse in 4 hours. Now, he quantified this to say that 1 horsepower is the amount of power required to lift 550 pounds by 1 foot in 1 second. For us, we will make make an equation or equality that 1 horsepower equals 746 watts. Now let's look at a few examples. 120 volts is applied to a motor and the motor draws 15 amps of current. What is the mechanical output of the motor? So we start with our equation, P equals V times I, and the output power in horsepower is 120 volts times 15 amps divided by the conversion factor of 746 watts per horsepower. So the output power of this motor is 2.41 horsepower. Another example, how much current is supplied to a 1/3 horsepower motor with a source voltage of 120 volts? So we start with the equation I equals P over V, and the output power of the motor will be our conversion factor, 746 watts per horsepower times 1/3 horsepower, and that's divided by 120 volts. The current supplied to the motor is 2.07 amps. Now, when we talk about mechanical systems and some electrical systems, we're quite often concerned with the efficiency of that system. Efficiency is symbolized with the Greek letter eta, ETA, and efficiency is expressed as a percentage. Mathematically, efficiency equals output power divided by input power times 100. Now, when you're doing some calculations regarding efficiency, understand that efficiency must always be less than 100%. There will always be some losses in our systems, be them electrical systems or mechanical systems. Let's look at a couple of examples. We're given that a 1/2 horsepower motor draws 3.89 amps of current from a 120 volt source. What is the efficiency of the motor? Well, we start with our equation for efficiency. Efficiency equals P out over P in times 100. Now the output power is 1/2 horsepower times 746 watts per horsepower divided by the input power, 120 volts times 3.89 amps, and this is multiplied times 100 to express the value of efficiency in percentage. So the efficiency of this motor is 79.9%. So we're losing almost 20% of the electrical power supplied in the form of heat. Now another example is that we have a power supply, a DC power supply in a guitar amplifier that's designed to supply an output of 5 amps at 24 volts. The efficiency of the power supply is stated at 80%. What is the input current to the power supply if the source voltage is 120 volts? We start with our efficiency equation. Efficiency equals P out over P in times 100. And we substitute in our known values. 80 equals the output power, 24 volts times 5 amps, divided by the input power, 120 volts times I in, times 100%. We solve for the input current, and that is 1.25 amps. So with respect to mechanical power and efficiency, these are the two equations that you need to know. 1 horsepower equals 746 watts, and efficiency expressed as a percentage equals output power divided by input power times 100.